Good evening. Great to have all of you in the room at the same time. I guess before we dive into today's class, I wanted to point out two things. One, I chose office hours I did on Monday from 3 to 5 because that's when the most people said they were available out of the entire week. I had 4 people come today, 4 people last week, so it seems like it works for some people. I don't know whether I should take that to mean that you guys feel very confident in the course material, everything that's been done up to now, or if it's that the time doesn't work, or that there's a lot of stuff going on, so it's difficult to make it come together. So if you do not feel extremely confident about the course material, I am in town until the end of the day Wednesday. So email me, schedule some time to meet tomorrow or Wednesday. I'm more than happy to make time. If it's late in the evening, tomorrow or tonight, I'll stay after class tonight. I don't have anything going on after class. So if you don't have lab, feel free to stick around and ask questions about either what we're doing now or what we've done in the past. We do have our second exam next Wednesday during class. It will cover everything up through Monday's class, so we will get into equilibrium a decent amount by then. The workshops, second thing to talk about is the workshops. I think, how many people did we have last Wednesday?
8.
8 people, 8 or so. That's great. That's about a third of the class, which is really good. But the second time slot, there were 0. So we need, I don't see as someone who's learning new material, being able to pass this class with strong confidence without attending workshops. We just do not have enough time in this class in order to get you the confidence and the skills that you need. That's why we try to work the workshops around your schedules and the polling that we've done in the past. You can work through those activities in office hours if you were to come to those, or in tutoring, or on your own. Whatever the venue is, that's fine. The challenge is that without working through those activities and gaining the extra confidence of those activities, I think it's going to be really hard to succeed going forward in the class. So I don't know how to help motivate you to go to those sessions or to provide sessions that work for more people. I know that there's a lot of other stuff going on in life. I just want to make sure that your money, your time, and your willpower you're investing in this class result in a maximum benefit. Which is why I try to not make it penalizing if you don't come, but I also want to make sure that it's encouraging that you do come. So I don't know if you have any suggestions for how we change this. How do we make it so that more people are able to come and they do come to office hours and to workshop? Are there any suggestions? Is everyone just super confident and doesn't need extra support, and so they're like, it's a waste of time? Okay, so how do I make it work for you all? And maybe if you don't want to voice up in the middle of class, when you stay after class, can you send me an email? Can you let me know? I'm trying to figure out how to support this class as much as humanly possible. But I need you all to tell me how to do that because I don't know your schedules, I don't know your lives. At the end of the semester, if you were unable to go to any workshops and didn't complete them on your own, I worry that you're going to be at a significant disadvantage. For instance, exam next week, there will be questions that come off of the workshop activities that have happened so far and that will happen this week as well. So, because they are what we're doing in class, it is not like extra material, it is practice on the material that we are doing in class. So this week, our workshop is going to be disrupted because we have the Friends of Science and Medicine seminar series. Can I maybe get a show of hands of how many people will go to Friends of Science and Medicine so we make sure that we figure out what to do with that time slot? So raise your hand if you're going 4:30 to 5:30, same time as workshop on Wednesday. Raise your hand if you're going to that seminar. So we have 1, 2, 3, 4, 5, 6. Are those all people that typically go to the workshop at that time? Raise your hand if that's the same time as you go to workshop. Okay, so at least a handful. So I think we will not have workshop Wednesday during that time slot. Instead of that, I would like to offer other times for a workshop, potentially between Wednesday's class and next week's exam so that you can get some practice on this material. Friday at 1 o'clock was a time that I was thinking about holding these. Would that be a time that people would go to this workshop? It's going to be Pogo Activity 39. It's going to be one about the topic we'll do in class on Wednesday. Would Friday at 1 work for anyone? Would you go to that? Raise your hand if you would go Friday at 1 p.m. 1, 2, 3, 4, 5, 6, 7. Okay, that looks like that time might work, so we'll do Friday at 1. Keep that in mind to one of the two of you. Hopefully that will work for one of the two of you. Yes? No?
Yeah.
Yes, could work. Could work. Okay. With Thursday evening, I don't know if that's...
Yeah, 6 to 8 is all I have.
Would between 6 and 8, either 6 to 7 or 7 to 8. Would that work for anyone who's not going Thursday or Friday at 1? Raise your hand if Thursday between 6 and 8 p.m. would work, either online or in person. No. The other time slot that I was thinking about is actually, doesn't work between classes, but Monday night. Half the class is in lab, but half the class is not in lab. So for those who don't go to lab, would you be willing to stay Monday night after class in order to go to workshop? Or Wednesday night? Raise your hand if that's a time slot that you would like, is Monday or Wednesday after class, if you do not have lab. That doesn't work either. Okay, please think about what might work. Please send me a note or talk to me after class to try to figure out how to support you. This class is about your success, and I need you to be an advocate for that. Okay. So today's class is going to be all about equilibrium. We're going to start to wrap our heads around what equilibrium means because there are tons of misconceptions. So please read through the entire, start on model. Let me see where we go. So skip over the first page, start on the second page, Model 2. Make sure to read, hardest thing to do, read everything on that first page, and then know what the titles are for the columns. And then once you've read everything, start answering the questions on the third page.
You skipping someone? Check.
Did you press start on that? Did you press start or whatever?
Yeah, next time. Dr. Alexandria and Catalogly was not on Wednesday. I just came in late. Maybe I haven't seen it.
They're not here.
So sometimes we I think the house brings immediately after the war, they're not available until, I guess, after to do that. I just want everybody to like all these signs and things we can submit them. There's a way to like change the immediately.
They should be for everything except for post-its. And the reason for post-its is that if you took those post-its and they wanted to see the answer to that question, it's
Yeah.
reasonable to, like, I don't think it's easy possibility to be able to just keep. Right.
Yeah, that's just a really good way to stay.
For sure. Absolutely. And as soon as one guy passes, then try to get
That doesn't have to happen.
Sorry.
So I have the first question under critical thinking question 4 up here, just to get us rolling and make sure we're on the right path. Nick and Kevin, I'm thinking for the sake of having more discussion, do you feel comfortable with the two of you? Do you talk a lot between you, or would you be up for me putting you in different groups to kind of have a bigger voice?
Sure.
Is that okay with you guys? So I think, Nick, can I put you at that back table? And then Kevin, can I put you, let's see, probably the best table is back there with Jesse Carter and those guys. That way we have 40 stable. Thanks for your flexibility, guys.
So since we're doing 0 to 1.
I'm gonna have Nick join this group if that's alright.
Since we would go in 0 to 1, you can just look at 0, and within that next 1 second, it says 2,500 of A.
Go ahead and grab a seat on the tables.
But
Do
it's
you mind
asking
if I
for
put
0
this
to
bag
1.
on one side or the other so I can sit down?
Of course.
Thank you. So how are we doing reading the table? Pretty straightforward?
Yeah. So this is like saying what it's starting with, right?
Mm-hmm.
And then this is how many reacted at 0.
Mm-hmm.
So then if it's from 0 to 1, would you add these?
So that is during each second.
Okay, so then would you subtract this from this?
So the question is it how many are changing or is it how many there are? And so those are two different columns, right? So the ones on the right are in the middle section there, number of molecules that will react. Those are the change. The columns, number of A, number of B, see how those are changed by that amount? So it's already doing the subtraction addition in those first two columns. You see that?
Wait, what?
So these two columns here, if molecules of A at the beginning is 10,000,
Yeah.
what is it at the next second?
7,000.
So what was the change?
2,500.
So would it be this one? Or
Yep.
Okay. So what would the...
So these numbers that react, the 2,500, the first column, you can see that in the second.
So is that the answer?
So it started out with 10,000, ended up with 7,500 because this many reacted, and this many became that.
So it's that. Oh, or no.
Which is what?
How many molecules reacted? Or is it 2,500?
So what's the group's decision? How many reacted during that first second?
2,500.
Yes.
Okay.
So the first few questions are just getting you oriented with the how to read that data in the table. So just keep going down that list of questions. This table's very quiet. Are we all answering the same thing? We checked with each other?
Not yet.
Okay, can we check? Looks like most people are kind of a little ways into it. Anybody want to take the lead?
So I got 2,500 for A and B, and then I'm on part 5, but I got 33 for part B so far. That's what I said.
Anyone have a different answer? Nope. Okay, sounds good. So we're on the right track. We're understanding how to read it. Kind of when it starts to get more complicated is down a little bit lower when it starts talking about fraction. Okay. All right, has everyone clicked in your answers to the first one? So let's just make sure we're all on the same page. Can I have a volunteer from Sarah Ray's table on how many molecules of A reacted in the first second?
So if you look at, so there's time and then there's number of A molecules. It starts at 10,000 at 0 seconds, and then at 1 second it goes to 7,500. So it drops 2,500.
Great. So we can confirm the 2,500 molecules of A reacted two different ways. One is Sarah Ray is talking about how many were there at 0 seconds, how many there were at 1 second. The difference is 2,500. That difference is also what's shown in, what is it, the fourth column, the number of molecules of A that react during that second. Okay? And then we'll not do the next one as a clicker question, but how many B are formed in that first second as well? Tracy?
25.
How do you know that? And why does that make sense?
It is in the little column that says number of B molecules formed, but also A reacts to form the B molecules, so.
Great, and it's a 1-to-1 stoichiometry, so every A that's consumed will generate 1 B. So this is one of the driest tables, but they're trying to simplify. They're not talking about this type of molecule makes this one. They're just saying something reacts, it forms one of the same thing. Why are those? We'll skip that. We'll go over the next thing. So go ahead and work through the rest up through critical thinking question 8, and then we'll pop in with some more questions as we go further on.
Number of B molecules that react,
In which time frame?
10 to 11. Is it the difference in the two, or is it just that total number?
Read this
Yeah,
really
the
carefully.
way that reads, it's like that. It would be that many
Yeah.
molecules. Okay.
Yep.
Okay. Yeah, I just wasn't know.
You're good.
Wasn't quite
It's a
sure.
good question.
Thank you.
It's all these questions are all orient us to the actual numbers there. So is the rest of the group on board with that value?
So that's the number of molecules that reacted. This number right here on the 11 second. That's how many reacted from that second to this second.
Well, so this is how many you have is this column.
Right.
So then this is how many of those are reacting.
Right. So the 708, it's down here on line 11,
Okay.
and that's
Remind me what the question is. Is it asking about 10 to 11?
yes, sir.
So it's 10 to 11, so it's in the next second at 10 seconds.
Right. And so
So it'd be the 10 line.
okay, and so this is the 10 line. That's how many reacted from 10 to 11. On
No.
the 10th line.
Yeah, this line is out of these many, 705 react in the next second.
Okay.
Hello.
Hello.
How are you doing?
Okay.
Did you grab one of the, I'll grab you a packet. Alright, so we're trying to get up to speed here. When you get a minute, listen to the recording after class, because the first 10 minutes we're talking about trying to, like, office hours, that kind of stuff.
Okay.
But I wanted everyone to start here.
Okay.
So read through this, and then go through the first page of questions on the next side, and ask your group to kind of help orient you if you get stuck at all.
One more thing, Dr. Barry. I wanted to talk to you about it on Wednesday, but so I planned on going and taking that ACS test on Friday, but then I got a call Thursday and they wanted me to come. I had to go to a funeral detail, so I wasn't able to take it. Will there be like another opportunity after the semester or something?
It's a once a spring kind of thing. So I don't think so, but send me that in an email, and I'll ask the department if that's something.
I'm just
that
making
they
sure. I don't
have,
want to be rude.
the ability to flex it.
Yes, sir.
I don't know the answer, so I can't answer that. But if you put it in an email, that one's easy for me to follow.
All right, I'll do that. Thank you.
For B,
Mm-hmm.
Would you do this divided by that number?
Mm-hmm. Because it's saying out of the however many you have, what portion are reacting, and so the number's going to be less than 1, because that's everything, right? So if you simplify down that fraction, what does it become for those? Did you guys do that as a simplified fraction for question 6? Gabby, why did you just let it go? What are you doing?
I'm sorry. There was a moment I was like,
I thought you were gonna do something with it. Did anyone do that? Simplify down the fractions? I'm still on this part.
The fraction.
Okay. Yep, that's what we're talking about.
So my question is are we just dividing it by everything that you have?
Yeah. So you're saying how many react out of your total?
Your total at that time?
Yep.
Or like at the whole So would it be like 33 divided by?
So think about this is the reaction that has 10,000 molecules of A to start with. And then 2,500 of those become B, so now you have 10,000 total, but some of them are B, some of them are A. So this number should always add up to 10,000. So it's not about adding these up, it's about at any time point, these two numbers add up to 10,000. All right, most people completed question 6.
If this one is reacting, do anything.
So we're gonna do a lot of these as non-clickers. What fraction of the molecules of A react between 0 and 1 second?
0.25.
A quarter, 0.25. What about the rest of the times? 0.25. Okay? So what happens as we have fewer and fewer molecules to start with? What happens to the number of molecules that react? It gets smaller. Okay? So this is a pattern I'm going to want you to think about. And then it's going to also ask about the molecules of B that react. So go ahead and keep working. If you've already gotten to question number 8, think about how you can use that to make predictions. That's what question number 8 is asking. And then go ahead and flip to the next page and start working through that. So when you're ready, go ahead and answer clicker question 12A. It's up on the screen. Feeling stressed or you all right?
I'm okay for right now. If I'm stressing back up the ramp.
Can you speak up a little bit more, Steph? You should be good.
Oh, yeah, I'm not trying to ask. Okay.
So, every time an A reacts to a year, just look at this. Every time one
Oh,
of
the
these
same
reacts.
amount?
So, in the first second, or 0 1 second, how many A reacts?
Or I mean,
Let's say you're ready now.
How many you have?
11 and 8.
And how many A's?
So
How many
25.
number of A that react in the next second is 2500. Which means you started with 10,000, you lost this many, got this many afterwards. Then how many D are formed? 0 to 2500.
Oh,
So
so,
that number over there.
oh, so that's one. Duh.
Close.
Should be the equal.
No,
But
not
they're
equilibrium.
reacting and kind of going.
So it's the same number consumed or the same number produced. So equilibrium means something very different. And that's because it's a one-to-one schedule.
Okay, yes.
Yes.
That makes sense.
So then here, you want to alter these numbers in? So looking at the time points, it's line 10. Go down here, it's from just at 10 seconds. Be careful because this is how many react in the next second. 10 to 11 is actually the same as 10. So this is how many start with.
It really is. There's just so many numbers. There's so many numbers. It's not, no lines. I had to put lines on that.
I was reading this too.
I had to line mine out because I was getting other numbers.
Yeah, so
This is how many A's in the next second. This is
reactions
how
still
many
going.
are reacting. So basically it's saying, although this is making this is also making this.
Okay,
So those reactions are starting to happen in both directions.
okay.
So that means that this, so this first second, you can't, why would no longer
Still gonna be
be
so
reaction at the beginning?
Because it's the program.
Yeah, but there aren't. What we're saying is the product will be reacting. So you have to have something to react.
To react.
Or-
Okay.
So it's not until you have some of these that you can start. So check all your answers as you go forward. All right, you still need a few more seconds to answer 12A?
I got 12A. Is it a?
Yeah, it's a clicker question. Go ahead and submit your response to 12A. You might be able to answer this before you even get there just by looking at the question. And if you do get there, then keep going. All right. Can I get a volunteer from Samantha's group? At what point did the reaction, or how long did it take to reach equilibrium?
Number of molecules that react with A and B stays constant. A becomes constant, B becomes constant.
Does everyone agree? 21 seconds?
I said 23.
Why 23 seconds versus 21, Michael?
Because the number of molecules in A and B would change at that point. They're still changing down too, even though the
So one thing that's a bit sneaky about this is the nuance between what Samantha and Michael are saying. And so if you look at how many of A are becoming B versus B are becoming A, that seems to happen a little bit sooner. But if you look at overall, when does the concentration of each stop changing? That doesn't happen until 23 seconds, I think. So if you look down the columns, there's a lot of information there. So can someone put in a very concise way, what does it mean to reach equilibrium?
Forward reaction equals the reverse reaction.
More specific. So Taylor said when the forward reaction equals a reverse reaction. What about those reactions?
The number of
They keep occurring at the same rate?
The rate of the forward reaction equals the rate of the reverse reaction. That means that during 1 second, 714 molecules of A become B. During that same second, 714 molecules of B do the opposite and become A. So what happens to the concentration of A and B after equilibrium? There's no change in the concentration of A or number of A or the number of B. But does that mean that the reaction has stopped?
No, they keep it up.
That is the biggest misconception that this activity is trying to uncover, is that a lot of people say equilibrium is when you have an equal concentration of both. That's not true. If you look at your numbers here, which one do you have more of at equilibrium? Is it A or is it B? We have a lot more of B, right? We have 7,000 compared to almost 3,000 of A. So equilibrium is reached when those rates of forward and reverse reaction are equal to each other. So go ahead and keep working through the activity.
So it is 21, 23 then?
23, I would say, is when equilibrium is reached because that is when the overall number of molecules, the net, does not change. And then I have question number 13 as a clicker as well. So go ahead and click in what the value of your KB is when you have that, and I'll look at the board when I see enough responses. We'll talk through that. If you get stuck, just flag one of us there. It's kind of splitting hairs because there's not a molecule that jumps ship. So read through the information before question 13 if you haven't already. Yeah. I'm trying to figure out. So yeah, it's asking me basically I find kicking this. Equation 1 is the one for parentheses. So the rate of conversion is equal to this KB times the number of molecules. So figure out what conversion is. And if you aren't sure what the rate of conversion is, then that's that big. I just have to fill everything in this and then isolate the
Better than using the first list.
number of molecules of B at any time. So it's asking you to use it. So pick something that then you have to have some big workload. Okay, so it seems like we're having a little bit of trouble with question 13. So think about, look at one line in the table. One line in the table says, in the next 1 second, that's your change in time, there are this many molecules reacting. It might be easier to go down towards the bottom because you know 714 molecules of B react per second, and then see how that compares to how many molecules of B you have to react.
Good teachers. Just kidding.
Oh. Hey, you don't know who I am.
Are we able to find the value of KB? Are you thinking that it looks like something else? Is that what you're pointing at?
It has to do with what we found.
I don't know how to figure out the units.
So think about units on both sides. So what is this? And what are units on this side? Molecules per second on one side. Molecules on the other. So K has to be per second. Okay, so I'm going to work through this on the board with everyone, and I'm going to ask for volunteers. Anyone figure out how to do this and kind of talk me through how we find KB?
Well, you gotta pick a time frame.
Okay, what time did you pick?
I picked the first 10 seconds.
Okay. The first 10 seconds, I'm going to guess you did the second 10 seconds. Because there's no B at time 0, so you can't find the change of B at 0 seconds. Correct?
Well, that's not what I did.
Okay. So maybe we'll have someone else talk through theirs, and then we'll see how it compared to yours, and we'll see if it gave us the same outcome, okay?
I think I did it the right way.
Okay.
I didn't, I
Can I get a volunteer?
We picked, closer down towards the bottom, and it's the number of B molecules that react per second was 714, and then we divided that by the total number of B molecules, which was 7,143, which gives you the KB.
So if we're using the exact equation on the front, it's 714 molecules are reacting per 1 second, right? And then that equals KB times the number of molecules that they existed. What's the number of molecules that existed at that time point?
7,143.
Okay. And so you're saying in order to solve for KB, you divided the left side by 7143 molecules of B. And then when you did that, you found that KB equals 0. Is it 10?
Yeah, I put 9.10 times 10 to the negative 2, so it would be 0.
Zero
Yeah,
point.
I mean pretty much if you round, but I did like that.
Okay, so it depends on how many sig figs we're using, what our answer would be. But it becomes approximately 0.10. Is that fair to say?
Mm-hmm.
What are the units?
It was
Seconds to the
Just a
minus
negative
1. Because the units on the left side have to equal the units on the right side. On the left side, we have molecules per second. On the right side, we only have molecules. So we have to have per second as the unit of KB. Okay? So does that number look familiar, 0.10? Yeah. It looks familiar from earlier on that page, right? That number, KB, tells us what fraction of the molecules react every second. That KB is the same KB that you talked about last Wednesday, that we talked about the 2 weeks prior. That is the rate constant KB. The rate constant says if it's first order, the more reactants we have, the more reaction we're going to get, the faster the rate of the reaction is. Is it the same rate constant for the reverse reaction, for if we find Ka? Do we think it's going to be the same rate constant? The rate is the same of the forward and the backwards when we get to equilibrium, but is the rate constant the same? If we had the same rate constant, we would actually end up with equilibrium being the same concentration of both reactants and products, but we don't. We end up with a lot more B, so that tells us something about the relative rate constant. So go ahead and work through the rest. Try to figure out what's the formula to find the rate, to explain the rate constant for Ka, and then find out what Ka is. Can you already guess what Ka is going to be? 0.25. So make sure that whatever you set up gives you that value that you've already found higher above. The next quick question I'm going to ask is for the exercise 2. So exercise 1, hopefully you can answer relatively quick once you've finished out the rest of this, and then we'll do exercise 2. Just me. I think the answer is no. All right, so if you haven't already, make sure you're on exercises. Exercise 1 is thinking about how do we put equilibrium in the sentence. Exercise 2 is about that new reaction. That's 2A form 1B. 30 more seconds to click in the answer for exercise 2A. Want to see where everyone's at? So that can move on. All right, I'm gonna go ahead and close this up. So, can I have one of the people that hasn't talked to this table yet explain how they got the answer? What you got?
I didn't get the answer.
You said you did or did not yet?
I did not.
Okay.
Except for A, 172 B molecules formed.
So you said you formed 172 B molecules, and how did you come up with that?
For every 2 A molecules, it produces 1 B molecule.
Great. For every 2 molecules of A that are consumed, we produce 1 of B. And so when the reaction goes in reverse, that stoichiometric coefficient comes into play. Okay. Great. And then can we follow through with the rest of them? So then it says how many, what's the next part of it? How many molecules of B will react in the next second? How can we figure that out?
It's going to be the same because they're at equilibrium.
So if we're at equilibrium, it means that the same number of B are consumed as were just produced, so the concentrations don't change. Okay. All right, let's go ahead and flip to the next page, activity 38. And before we get into this, pause. That packet we just looked at was all in number of molecules. The exact same data is now portrayed, but there's concentration instead of number of molecules. Okay, so as you look at that new table, don't be like, oh my god, there's all this new information. Say, okay, it's the same information, but now they're talking with a specific volume in mind. What's the concentration, and looking at how concentration changes with time. So make sure to read carefully through the first 2 pages. That information on the first page is going to be really critical. And then once you're ready, start answering the next set of questions. So I just had a very good question. What does this mean around a number? When they put parentheses around the number? Concentration in molarity. This is a very unique utilization of those parentheses. Usually, what kind of parentheses do you see? Square brackets. So this particular set of activities, these POGL activities, they use both for molarity, but they're not the same. The top one is molarity, any molarity. It can be just looking at the beginning of a reaction, the end, it doesn't matter. The bottom one, the square brackets, they use specifically for the concentration at equilibrium. Then they use those square brackets. Okay? This is unique, and there is a very good reason that they do this. So think about the last set of problems you're looking at, that the concentration up until 23 seconds, we would use the top parentheses. The concentration past 23 seconds, we would use the square brackets. Okay? So you'll see more of that as we start working through this activity. So keep that in mind as you start working through it.
He started with
Five, six.
So just be really careful to not, statement that you made is fantastic because it allows us to always start the process of those challenging things, we have to figure out how to do that, and that's gonna apply, yes, essentially just asking you to. So, once you know what you need to use, map it. So that's, don't trick yourself and say, oh, if I see how to start it, then I can. So this one is just saying, show them. So we want to figure out how to show concentration is. So we know our concentration.
Intuitive way to do it. I came out with a number that's nicely concentration.
So we read through all of this, as we did. So we basically, find the units of concentration per liter.
So here's Kenny, so we had a day.
So for this type of problem, where it's basically saying, look at the graph and make sure it's right.
This one, so this is kind of orienting yourself at least in the graph here. Polarity, molecules like that.
So
So it's gonna just put the molecules to the left.
and then once you have that, it's going to apply that. Now it's not just what's the polarity, it's what's the rate. So what's the difference? The first question to ask about polarity. Concentration is rate. What's the difference in that one?
We start out with the volume.
Because it's the same.
Start out. I did, we was 1 liter for 1 liter, there's 0.0369 moles, and for every 1 mole is that many molecules. And that would be, either way, it shows that it's got to be the same.
It's a little bit harder to get oriented with this table. Concentration is a little more complex than just the number of them. So when you're ready, put in your answer to question, critical thinking question 3, which is what is the forward rate at concentration when you're at 5 seconds. And it is alphanumeric, so make sure you have the right units. You have a migraine? Class is recorded. I was trying to work on this after. You can ping me afterwards, right? I feel like you have to.
I'm gonna go get another one. I'm sorry. Not the right thing, because it does not come.
Yeah, I have my calculator, but not good. But I'll write it down.
So think about times 10 to the what? Or is that the actual value? And then think about the units. So at the top you has moles. This is moles. Choose moles. And what is that? The unit of that. And it's per liter. Okay. So you're do big M right hand. All right, can I have someone walk me through how we would answer critical thinking question 3? So how would we find the forward rate when we're at 5 seconds? Aisling, do you want to talk me through that?
So, to find the forward rate, you multiply Ka times the concentration of A at 5 seconds.
And what did you find that to be?
0.25 times 0.0369.
And you found?
0.00923.
Units? So it helps if we put our units in when we did the initial calculation. So 0.0369 is molarity. The units of our rate constant were per second. That's what we figured out previously, and it has written on the last page. So it's molarity per second. Does that number make sense? How do we check that number?
Put it into the graph and then see if it's like logically descending.
So if we had a graph, yeah, or the table. Yeah.
That's what I'm.
So I think that's what the table behind you did as well. So we put it into the table. We look to see, does that number make sense sequentially as time is going by? And so it helps if we rewrite it in scientific notation. So we could either do 9, or I guess if we do times 10 to the negative second, 0.923 times 10 to the negative second, molarity per second. Okay. Can you figure out the rate of, so that's the rate of the forward reaction. Can you figure out the rate of the reverse reaction as well? Same idea. Is it the same rate constant? Rate constant is 0.10 per second there. We can kind of use that to move forward. So, are we at equilibrium at 5 seconds? We are not at equilibrium at 5 seconds. How do we know that? So Alexandra is saying the concentrations of A and B are still changing, and they are not at a steady state yet. So for the sake of time, I want us to go ahead and jump to the next page. Look at the graph. All right, I want you to, in your tables, amongst your table, to look at that graph. Try to figure out what part of that shows the kinetic phase or region, what part shows the equilibrium phase or region, and highlight that on your page. And discuss with your table why you're defining one region as kinetic and one region as equilibrium. And then with that done, go ahead and start answering question 7 and below. Do I have a volunteer that wants to highlight on the tablet? Kinetic and equilibrium? Thanks, Stacy.
Do I just like draw a line and?
Sure.
Okay.
Okay. So why did you pick that time point and to put kinetic on the left side and equilibrium on the right side?
At least from what I can see, it looks like the concentrations are changing on the left side, and then on the right side, they're static. So.
Great. So the reaction is over at about 16 seconds, is that right? No more reaction happens.
No.
No. The reaction keeps going, but it keeps going at a rate that is the same for the forward and the reverse reaction. So the big picture, when you zoom out, it looks like there's no reaction happening. That's what happens when you get to equilibrium, is that it looks like the concentrations, because the concentrations, thank you, don't change, it makes us think that the reaction is not occurring anymore. So with that in mind, go ahead and look at what the ratio is for concentration in B to A at each of the time points. It's asking you to do an approximation by looking at the graph. So go ahead and as quickly as you can, answer question 8. Just think about the ratios. Just approximate, eyeball. Do it quickly. It's quick and dirty.
Yeah, possibly. We can't see. Is that why that's 16?
Yeah, because it looks like it's not
Yeah,
quite at
I've
the
seen
top
like
yet.
right there, there's a little bit of.
All right, what are we finding about that ratio? Is that ratio staying constant or is it changing? Amber? It changes from the beginning, so it starts out asking about, was it 10 seconds, or 1 second, 4 second, 15, 20, and 40. And if you look at the next page, it'll ask you to go back to the actual data in the table. This is actually plotting the reaction we've been looking at the whole time. And it says, we can confirm it now by looking at specific numbers of the concentration of the reactants and products. So one of the concepts that I'm going to introduce to you now that we're going to have on your pre-class quiz for Wednesday, and we're going to spend class on Wednesday working on, it's called the equilibrium constant. We're going to have to start being really careful whether we have an uppercase or a lowercase k. The uppercase k is the new equilibrium constant. So far, it's all been lowercase. So the equilibrium constant, and I think you did have this in your primer, is that right?
Yes.
All right, so how would we find the equilibrium constant for this reaction? It's a fraction. What goes on the top? What goes on the bottom?
Concentration of the reactant divided by the concentration of the product.
So close. Concentration of the product over concentration of the reactant. And it's a little more complicated than that too. What's a little more complicated? Raised to its stoichiometric coefficient. So at equilibrium, we have a concentration. So I'm going to do this. This only applies for square brackets. So it's square brackets of product over square brackets of reactant. Remember, we said the square bracket means at equilibrium, raised to the stoichiometric coefficient. So for this particular reaction, what is our equilibrium constant? Can you guys go ahead and calculate that? Go ahead and calculate what is our stoichiometric coefficient for both these reactants and products? It's 1 and 1. So don't worry about that for this reaction. So what is that ratio? 0.0714 over 0.0286. Can anyone put that in a calculator? Who's the fastest gun in the West? 2.50. Does that sound right? Does that match what other people had? All right, so the equilibrium constant tells you a lot. It doesn't tell you anything about the left side of the equation at all. This reaction, it doesn't tell you about the kinetic phase. But it says once the reaction gets to equilibrium and we don't have a consistent change in the net concentrations, it says, what are we going to favor? The reactant or the product? If the number is bigger than 1, what do we favor? Reactant or product? If this ratio is bigger than 1, what do we favor? Product. The thing on top is bigger than the thing on the bottom. Equilibrium constant says that at equilibrium, 2.50, I always make it into a fraction even if it gives it to the whole number, because it says it's going to be that over 1. It says that at equilibrium we have 2.5 products for every 1 reactant. This holds true if it's a stoichiometric coefficient of 1. Stoichiometric coefficient is 2 for one of them, then you would square what's on top, right? If it was a 2 for the products was a stoichiometric coefficient, you would have to square this. And then it's not quite as proportionate. But the most important thing to keep in mind about this equilibrium constant is we're going to be working with numbers that are much, much bigger or smaller than 1. 1 is kind of between 1 and 10, tells you that they're pretty close in concentration to each other at equilibrium. We're going to have equilibrium constants that are like 10 to the 15th. That's a 1 with 14 zeros after it. That says that you have a ton more of one thing than the other at equilibrium. 10 to the negative 12th means that you have 10 to the 12th on the bottom and 1 on the top. Okay? So I want you thinking about what does this mean when the reaction finishes its kinetic phase, gets into the equilibrium phase, how much of each are we going to have? And by the way, 2.50, does that number look familiar? If you think about our rate constants for this reaction, what were they? 0.25 and 0.1. What is the ratio of those? 2.50, our equilibrium constant. So the rate constant, the forward and reverse rate constant actually dictate the equilibrium constant. And then that tells us how fast they get there and then what they are going to be once they get there. So you'll have a little bit more of this at your primer for Wednesday. And anything before equilibrium is called the reaction quotient. Anything after equilibrium is called the equilibrium constant. Q and K. We'll be working on that in class on Wednesday.